After this example, let's see another important concept, that is of what do you mean by L about a point and what do you mean by L about an axis. These are two related concepts, but they are different, and we should be very clear how they are different. You see, we had seen that what is that angular momentum about a point is given by L is equal to R cross P. This is for an ith particle, this is for the whole body by using the summation, and this angular momentum is perpendicular to that plane of xy motion. This is very clear. So this is angular momentum about a point, about an origin O. In this case, I am calculating my angular momentum about this point O. This is my origin. Now if somebody says that okay, find out what is angular momentum about an axis. The moment somebody asks you, say find L about an axis, suppose in this case L about z axis, there are three steps. Number one, take any point on axis as origin. Now mark my word, any. It means I can take any point as origin. Number one is take any point on axis as origin. Number two step is find L about this point using the formula L is equal to R cross P. Then third step, you find the component of this L, whichever L you have found out on this point along the axis, you find the component of L along the axis. So this is a three-step process to find L about a particular axis. Now there are 2-3 points about this thing. First of all, you will say ki how come if I take any point on this axis I will get the same answer. That's it. Suppose I have to find out say LZ. Okay. It does not make any difference whether my O is here or my O is here, here or anywhere down here. As long as that origin, that point is on the axis, the answer will be same. So how it is same, I will explain in the next slide. And then after you have chosen any particular, any arbitrary origin, you use this very simple L is equal to R cross P formula. After finding this L, what you do? You take component of this L which is along this axis. So if suppose I may get L as say 4i plus 6j plus 19k. Now I have to find out L about an axis, that is L about say z axis, then my LZ will be 19. Remember, L about an axis, the moment you are taking about an axis, it becomes a scalar. If you are finding L about a point, it is a vector, and LZ, that is the L about an axis, is the particular component of that vector. Now that's you would have understood this thing, but still I have to explain how does that this any point, how the choice of origin does not make any difference. I will explain that right now. You see, suppose this is my z axis and I have to find out L about this z axis. This is my x, this is my y, this is my particle which is moving with linear momentum p, and this is my position vector with respect to O. This is my origin. Now I am saying, I am claiming that no matter where I choose my O, I can choose my O here, here, this LZ will be same. How? See, I can write this R as R perpendicular plus R parallel. Remember, I told you this formula is very important. This method is very important, how to break any R into two components. I have written R as R is equal to R perpendicular plus R parallel. I have to find L. So L will be R cross P, will be R perpendicular plus R parallel cross P. So this is the thing. So this is my L. Now you see what will happen. I have to find component of L along the axis. Now see this second bracket, whatever it is contribution, there will be some contribution, but that contribution will be perpendicular to the axis. Why? Because you see this R parallel, this thing is parallel to the axis. So whatever be the cross product of this R parallel and this P, it will be something in this direction or here, whatever, it will be perpendicular to the direction of Z axis. So when I am finding the component of L along the axis, the Z axis, this thing will not give me any contribution. This thing will be giving me 0. So my answer for LZ will only depend upon this component, because this R parallel cross P, although it will be having a non-zero value, but it will be something like say 4i plus 16j. Now 4i plus 16j is not going to make any difference to my Lj. For my Lj, this is null and void, this is useless. That's what I was telling, that this answer, the answer of Lz does not depend upon this R perpendicular. So if I take my origin here or somewhere here, what will happen? Only this R perpendicular will change. So R perpendicular, the change in R perpendicular is of no consequence to Lz. So Lz only depends upon this perpendicular distance. So this Lz, that is the Z component of L or the component of L along the axis, this Lz does not depend upon this R parallel. Why? Because this R parallel cross P will give something, but that something will be perpendicular to this axis. So it is not going to make any difference to my Lz. Now we were dealing with angular momentum L. Now let's deal with the aspect, the dynamical aspect of this L. That why does this L change, or how does this L come into picture? Now in Newtonian mechanics, you would have seen that when you are having linear momentum, say P, then what causes change in P? That is caused by force, that is force is equal to dP by dt. So the next question is, do we have something similar for angular momentum? And the answer is yes. Suppose you have been given a point mass, the simplest case I am dealing with, and the origin is fixed, that is this is my mass M. So this is my mass M, this is my origin, this is my R, and this is my P. So what will be L? L will be R cross P. Now I will find out the derivative of this L, that is dL by dt will be d by dt R cross P. Using the rule for cross product derivative, it will become dr by dt cross P plus R cross dP by dt. Now you see this thing, what is dr by dt? Dr by dt is V. So this V, cross product of two vectors is 0, so you will get 0 plus R cross F. So what I have got? I have got that dl by dt is something called R cross F. So let's give some name to this R cross F, and the name is given as torque. So torque is defined as R cross F. Basically, what is torque? Torque, it is the turning effect of a force. When you are applying force on something, the object may turn. How much it will turn? That depends upon this quantity. Torque is equal to R cross F. This is the definition. Using this derivation, what I have done, I have proved that torque is also equal to dL by dt. Remember, this is for a very special case of point mass and fixed origin. Don't generalize this formula for any kind of body, you will fail. So this is torque is equal to R cross F. So let's see what is this torque in greater detail. This torque is basically the turning effect of force. This is defined as R cross F. Suppose this is a wrench and you have to turn about this origin. So this is my R. I am applying a force F. So what is happening? This perpendicular component that is tending to rotate, because this component F cos phi, if I am applying a force in this direction, then it will not rotate. Whatever is the component in this direction, that is contribution of this force towards this rotation. So that's why this torque is also Rf sin phi, or I can write sin phi as this distance d, which is also called lever arm. So torque is equal to F into d, or this the same thing, whatever tricks and methods we used for calculation of L, because what was L? L was R cross P. So the same methods we can use for calculating torque also. Torque is equal to R cross F. Just in case of P, instead of P, we will be writing F here. Similarly, you see this R cross F, so magnitude will be Rf sin phi. Now this torque will be in a plane perpendicular to this motion. This is this R and F. So this is my R, this is my F. So torque will be in this perpendicular direction. It has been shown here. This torque will be R cross F. So this is in perpendicular to this XY plane. So now we saw for one case, that case was for a point mass and a fixed origin. Now suppose I have been given a extended mass. By extended mass, what do you mean? That okay, there are many mass of mi is the mass of one particular particle. So basically you have got a collection of particles. So whether there is something like torque is equal to dl by dt for a collection of particles also? Answer is yes. You see how it will come. For a collection of particles, my L will be summation Ri cross Pi. Now we have seen that in Newton's second law derivation for a collection of particles, what was this? Fi external plus Fi internal is equal to dpi by dt, that is Pi is the momentum of ith particle. So when I write this dl by dt, it will become d by dt of, this is my L, summation Ri cross Pi. Now I open this bracket, I will get this thing plus this thing. Now dr by dt will be Vi, and this Vi cross Vi, the cross product of two parallel or two same vectors is 0. So this Vi cross Vi, MVi will be 0. So this thing will become 0. So now you get this second summation. What is this second summation? This will be summation Ri cross, now dpi by dt, that is what is the rate of change of linear momentum of a particular mass, ith mass. That will be the external force plus the internal force on ith particle. Now when you do this summation, this Ri cross Fi internal, that will come out to 0. Why this will go to 0? I will prove in the next slide. So ultimately what you will have, that dl by dt will be summation Ri cross Fi external, which I can write as the external torque or the torque due to all the external forces. So this is something very similar to the cases we dealt with in center of mass chapter, that F external we had there, that F external is equal to dp or d mass of center of mass into velocity of center of mass by t. So similarly we are having for this case also, that is the total angular momentum dl by dt is equal to torque I external. Now only thing I have to prove this part of the derivation. So let's prove this part also. You see what is happening. Suppose this is my first particle, this is my second particle. The internal forces due to Newton's third law will be acting in, they are equal in magnitude but opposite in direction. That's what Newton's third law says. Here we will be assuming a stronger version of Newton's third law. Not only they are equal in magnitude and opposite in direction, they are also acting along the line joining these two particles. So what will happen, this torque 1 plus torque 2, that will be R1 cross F21 plus R2 cross F12. Now this F12 is equal to minus of F21 from Newton's third law. So when you do this addition, ultimately you will get R1 minus R2 cross F21. Now you see what I have assumed, this is an assumption that this F21, this internal force, is acting in a direction which is along this R1 minus R2, that is the whatever internal force is acting, that is acting along this direction. So if these two vectors are in same direction, or it's a parallel or anti-parallel direction, their cross product will be 0. So when you are adding similar product pairs for different particles, summation of this will become, summation of 0 will become 0. So your all internal torque, that is summation of torque internal, will be 0. So in that equation what we get? We get only the net external torque, that is causing change in angular momentum. So this I have written it here, that is T naught net, that is net torque external will be dl system by dt. And similar, so we can get an equation of conservation of angular momentum also, that if torque, external torque acting is 0, so the angular momentum of the system will be constant. That is, if the net external torque acting on a system about some point is 0, the total angular momentum of the system about that point remains constant, that is L system is equal to constant. So this is the conservation of angular momentum. So remember, till now I have proved that this torque is equal to dl by dt for a point mass also, or for any collection of mass also. This is the same derivation I have used for discrete collection of particles. If they are continuous body, so instead of summation I will have integral, the derivation will be exactly same. Now my question is, this torque is equal to dl by dt, under what circumstance will this equation be true or valid? number one assumption is कि obviously suppose this torque is calculated about O, this L has to also to be calculated about O, that is the origin has to be the same. It cannot be that you are calculating torque about say this point O1 and you are calculating L about O2. You are calculating torque about O1 and L about O2, then this thing will not remain true. So that is number one thing. So I have seen that this torque is equal to dl by dt will hold only if on both sides LHS and RHS you are using the same origin O. Like if you are calculating about O, if you are calculating torque about O, then about same O you have to calculate L also. Number one. Number two, suppose I say that this O is not fixed, it is O is moving with velocity v, then can this equation hold true? The answer is yes. If the origin about which I am calculating my torque and L, suppose this is my origin, if this origin is moving also, as long as it is moving with constant velocity, this equation will be valid. Now come to the third stage, third question. Suppose instead of moving with constant velocity, if it is moving say with acceleration A, then will this equation hold true? Now it has got 2-3 cases whether can it hold true or not, but in general I will say that if your origin about which you are calculating torque and L, if it is under acceleration, this equation will not hold true. This will fail. Very simple answer. Why it will fail? Because the moment your origin is accelerating, what is happening? You have entered into the realm of non-inertial frame of reference. So you will have to deal with pseudo forces, that is MA. And you would have seen that while calculating this torque, we never talked about pseudo forces. So that's why when your origin is accelerating, this equation will not hold true in general. But there is one very interesting and one particular case. That is what will happen if suppose this origin, although it is accelerating, but this origin happens to be my center of mass. In that case I will say this equation will hold, that is torque about center of mass will be dl about center of mass by dt, even when this center of mass is accelerating. Now that is the beauty, that is the whole beauty of center of mass, that even if this guy is accelerating, this equation will hold true. That's why most of the calculation we are doing, we are concentrating on center of mass, because this guy has got very beautiful properties. It saves our life on so many occasions. Now why it happens that okay, if this torque is about center of mass, then this equation will hold true. Now you see why it happens that when the origin is center of mass, then even when this origin or this center of mass is accelerating, I can use this equation of torque is equal to dl by dt. You see, suppose I have got a body. This is a collection of different particles given here. Now just consider say gravitational force. Now each gravitational force can be represented by this green line, that is MIG. Now each particle is being attracted by this Mi is the mass of the particle and G acceleration due to gravity. But when we are dealing with say a collection of particle or a continuous mass, each of these individual forces can be represented by one single force acting on center of mass. That is, this is my center of mass, and I can represent that okay, there are different particles and different MIG, but the total of this MIG is capital M into Z acting on center of mass. In a collection of particles, this is my particle, different places. Now when this body is accelerating, or say this is my center of mass, about this origin I am calculating, and this is accelerating. So each particle will be experiencing a force given by MIA. Okay, that is the pseudo force. Now the summation of these MIA can be represented by a single force acting on center of mass and given by MA. Now this will be minus if you take the vector form, because if your A is in this direction, pseudo force will be acting in backward direction. So what happens? The total pseudo force, the net pseudo force will be acting on center of mass. Now since this force is acting on center of mass itself, torque due to this thing about center of mass will be, what is torque? Torque is R cross F. Now although this F is there, but this F is acting on this thing itself, so your R is 0. R is 0, so torque is 0. So because of this pseudo force, there is no additional torque being added in this equation. That's why this equation will hold if you are calculating this torque and L about center of mass. So this is the answer why this will hold. But I will give you a very rigorous answer, derivation also of this thing. It is appears to be quite complicated and lengthy, but it is not that if you just get a hang of what is happening there. Suppose I have been given an extended mass and this is non-fixed origin, that is, this is my origin, but this origin is accelerating or moving. So what will be L? L will be summation Ri minus R0 cross Mi Ri dot minus R0 dot. This will become dl by dt. Now when I find this dl by dt, this derivative will become dot dot. Now this is same as this, so their cross product will be 0. So first bracket has gone to 0. Now concentrate on the second bracket. This will be Ri minus R0 cross Mi Ri dot. Now what is this thing? Ri dot we had used earlier. This is the acceleration of the ith particle. What will be that? That will be Fi external plus Fi internal. So this also I know, minus Mi R0 double dot. This is the acceleration of the origin. Now what will happen in next step? You see, when I open this bracket, what I will get is summation Ri minus R0 cross Fi external I will get. Now this Fi internal will be 0, as I had seen in the earlier case also, because this internal torque will be 0 because of Newton's third law. Then next bracket, this next will be minus summation Ri minus R0 and this Mi R0 double dot. Okay, now you find out this, what is this Mi Ri summation? This is the definition of center of mass. So this Mi Ri I can write as is equal to Mr, where R is center of mass. So this will become minus, this is become minus capital M R, and this term I can write it as, so you see what I have now, this bracket, if you, when you expand Ri minus R0 cross this thing, this Fi internal will become 0. So I am not worried about these two things. Let's expand this thing multiplied by this thing. What will happen? This will be summation Ri minus R0 cross this thing. When you expand this, you will get Mi Ri minus Mi R0 cross R0 double dot. Now this Mi Ri is nothing but capital M into R, where R is the position vector of center of mass. So this will become Mr. Now when you do this Mi summation, you will get capital M, and this R0 is constant, so you will get Mr minus Mr0, and now this cross R0 double dot will remain. So I can write it as minus capital M I have taken out, bracket, R is the position vector of center of mass, R minus R0 cross R0 double dot. So this is the contribution of this thing when you multiply this with this. So when I write the whole thing, it will become you see, that's the exactly same thing I have written, that dl by dt will be summation Ri minus R0 cross Fi external. This term is the old term which we had seen earlier also. This Fi internal will become 0 because of Newton's third law, minus capital M R minus R0 cross R0 double dot. So this is a pretty dangerous looking formula. and believe me, you will never use this formula. There will be no occasion for using this formula. But you see, what does this say? I can use this formula and derive this thing. dl by dt will be torque I external under what circumstances? Under circumstances when this thing goes to 0. Now when it goes to 0, it can go to 0 in 3 cases. Number 1 is r is equal to r0. When r is equal to r0, this whole thing will become 0. That is, if my origin is the center of mass, I will get back to my old, pretty old, beautiful little formula, that is dl by dt will be torque external. That's why I derived during using other methods also, that when your origin is center of mass, even if it is accelerating, your the dl by dt is equal to torque external will hold true. This is one case. Another case will be r0 double dot is 0, that is your origin is not accelerating. That's very simple. If it is 0, that is your origin is not accelerating, you will get this thing. And third case will be when these two vectors, if they are cross product, so if they are parallel, their cross product will be 0. Now basically what it says, I can use my dl by dt is equal to torque external formula if I am calculating my torque and origin about a safe origin. Safe origin meaning either the origin should be center of mass or it should be non-accelerating, that is the origin should not accelerate.